In the early years of the 20th century, science stood on a trembling bridge between two worlds: the old, familiar world of Newton's clockwork universe, and the strange, unpredictable realm of the quantum. It was a time when the atom, once thought to be the smallest indivisible particle of matter, began to reveal secrets that shattered centuries of understanding. Amid this intellectual storm rose a quiet, contemplative Danish physicist named Niels Bohr, a man whose ideas would redraw the map of reality itself. Bohr's atomic model was not merely a scientific theory, it was a revolution of thought, a bridge that carried humanity from classical certainty into the mysterious territory of quantum behavior. To understand what made Bohr's model so transformative, one must first imagine the scientific landscape that preceded it. For over 2,000 years, thinkers had pondered the structure of matter. The ancient Greek philosopher Democritus proposed that all things were composed of tiny, indivisible atoms. Centuries later, John Dalton's atomic theory revived that idea with a chemical twist. Atoms of different elements combined in fixed ratios to form compounds. But Dalton's atoms were like solid billiard balls, simple and featureless. By the late 19th century, discoveries in electricity and magnetism began to chip away at this solid vision. J.J. Thomson's identification of the electron in 1897 revealed that atoms were not indivisible after all, they had internal structure. Thomson's own atomic model, often called the plum pudding model, pictured the atom as a sphere of positive charge studded with negatively charged electrons, like raisins in a pudding. For a time, it seemed to explain the atom's neutrality and basic behavior. But then came Ernest Rutherford's gold foil experiment in 1909, a breakthrough that changed everything. When alpha particles were fired at thin sheets of gold, most passed through as expected, but a few were deflected sharply backward. It was as though bullets had bounced off an invisible wall. Rutherford concluded that the atom must have a tiny, dense, positively charged nucleus at its center, around which electrons move. Yet this new nuclear model posed a terrible problem. According to classical physics, an electron orbiting a nucleus should constantly lose energy by emitting electromagnetic radiation. As it loses energy, it should spiral inward and collapse into the nucleus, meaning atoms, as we know them, should not even exist. Clearly, something was wrong. Nature's atoms were stable, and that stability defied the known laws of physics. Into this puzzle stepped Niels Bohr, a young Danish physicist who had been working under Rutherford in Manchester. Bohr was deeply thoughtful, a man who balanced scientific rigor with philosophical curiosity. He was fascinated by the new quantum ideas introduced by Max Planck and Albert Einstein. Planck had shown that energy was not continuous but came in discrete packets called quanta. Einstein extended this concept to light, explaining the photoelectric effect by suggesting that light itself behaves as particles, photons. Bohr wondered, could this quantum concept also explain the structure of the atom? In 1913, Bohr published his theory of the hydrogen atom, and with it, he transformed physics forever. He proposed that electrons move around the nucleus in fixed orbits, each corresponding to a particular energy level. These orbits, or quantized shells, were stable, meaning electrons did not radiate energy while moving in them. They could, however, jump between levels by absorbing or emitting a quantum of energy, known as a photon. The amount of energy released or absorbed matched the difference between the two energy levels. This simple but radical idea elegantly explained the spectral lines of hydrogen that had puzzled scientists for decades. When hydrogen gas is heated or excited, it emits light at specific wavelengths, a phenomenon observed as bright lines on a spectrum. Classical physics could not explain why only certain wavelengths appeared, but Bohr's model made perfect sense of it. Each spectral line represented an electron transitioning between energy levels. The Balmer series of hydrogen spectral lines, once an empirical curiosity, now had a theoretical foundation. For the first time, scientists could visualize the atom not as a random swirl of particles, but as a miniature solar system governed by quantum rules. Bohr's atom was at once familiar and revolutionary. It retained the planetary motion of Rutherford's model, but it introduced a strange new logic, a logic in which only certain orbits were allowed, and energy was not continuous but discrete. In the space between the orbits, the electron could not exist. It was a daring combination of classical imagery and quantum principle, a marriage of the visible and the invisible. The impact of Bohr's model was immediate and profound. It solved the mystery of atomic spectra, gave new meaning to quantum theory, and set the stage for the later development of quantum mechanics. But more than that, it represented a new way of thinking about nature. Bohr's atom was not just a model of matter, it was a model of how knowledge itself must adapt to the mysteries of the universe. In his quiet Copenhagen study, Bohr wrestled with questions that went beyond mathematics. He sought not just to describe the atom, but to understand what its behavior meant. How could something so tiny obey such strange rules? How could reality itself be discontinuous, jumping from one level to another? The deeper Bohr delved, the more he realized that the quantum world defied human intuition. Yet he never saw this as a failure of science, rather as an invitation to expand the boundaries of thought. The elegance of Bohr's model lay in its simplicity, but its beauty was matched by its philosophical depth. He recognized that the act of measurement and observation played a role in defining what could be known about a system. Though this idea would later be formalized in quantum mechanics, the seeds of it were present even in his early atomic theory. To Bohr, science was not about uncovering an objective, detached reality, it was about describing what can be observed under specific conditions. In 1913, when Bohr's paper was first published in Philosophical magazine, the scientific community reacted with both astonishment and skepticism. Some dismissed it as a strange hybrid of physics and metaphysics. Others, like Einstein, admired its brilliance even while questioning its assumptions. But the true power of Bohr's model was in its predictive accuracy. When tested against experimental data, it matched perfectly, a clear sign that Bohr had touched upon something real, even if its full meaning was not yet understood. Bohr's theory not only explained hydrogen's spectrum, but also provided a framework that could be extended to other elements. The concept of quantized energy levels became the foundation of atomic physics. Over time, refinements were made by scientists such as Arnold Sommerfeld, who introduced elliptical orbits and relativistic corrections. These extensions deepened the model's precision, but its heart, Bohr's central idea of quantization, remained intact. The world was witnessing a paradigm shift. The atom was no longer a simple, solid sphere, nor a miniature solar system obeying Newton's laws. It was a quantum entity, its behavior governed by probabilities, energy jumps, and strange discontinuities. Bohr's model marked the first true bridge between the tangible and the abstract, between the world we see and the hidden one we could only infer. What made Bohr's contribution truly remarkable was his ability to hold contradictory ideas in harmony. He respected the rigor of classical mechanics but was not afraid to transcend it. He valued logic, yet embraced mystery. This intellectual balance became a defining feature of his character and his science. He once said, "The opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth." This was not just philosophy. It was the guiding spirit of his approach to physics. The years following 1913 saw Bohr's atomic model gain widespread acceptance. It became the cornerstone of chemistry, explaining why atoms form particular bonds and why elements have specific properties. It illuminated the periodic table in a new light, showing that chemical behavior was governed by the arrangement of electrons in their quantized shells. Suddenly, the complex tapestry of matter seemed woven from a simple, elegant pattern of orbits and energies. But beneath the surface of this success, Bohr sensed that his model was only a stepping stone, a beautiful approximation, not the final truth. As experimental techniques advanced, new phenomena emerged that the Bohr model could not fully explain, such as the fine details of spectral lines and the behavior of multi-electron atoms. These challenges did not discourage Bohr, rather, they inspired him to go further, to refine the quantum concept and explore its philosophical depths. Still, for its time, the Bohr model represented a monumental leap in human understanding. It turned invisible patterns of light into keys that unlocked the structure of matter. It transformed the atom from an abstract idea into a quantized system that could be mathematically described. More profoundly, it forced scientists to rethink what it means to understand something in nature. No longer could physics rely solely on visual models or mechanical analogies. The atom demanded a new language, the language of quantum theory. As the world moved through the turbulence of war and discovery, Bohr's ideas spread far beyond the laboratory. His model inspired artists, philosophers, and even poets who saw in it a reflection of life's dualities: stability and change, certainty and mystery. To many, Bohr's atom was a metaphor for the human condition, bound by rules, yet capable of sudden leaps into the unknown. Bohr himself remained humble in the face of his achievements. He often credited others, from Planck to Rutherford, for paving the way. But history would remember that it was Bohr who gave the atom its quantum soul. He had transformed a collapsing model into a living, stable universe of energy and motion. His atomic vision stood as a monument to human curiosity, a reminder that even in the smallest spaces, entire worlds await discovery. As night fell over Copenhagen in those early years of the 20th century, one can imagine Bohr gazing out his window, his mind still orbiting the mysteries of the atom. The lights of the city flickered like tiny electrons, stable, radiant, and full of possibility. In their glow, Bohr saw not just atoms, but the essence of the universe itself, a dance of energy, a harmony of structure and uncertainty. And so began a new era of physics, an era in which the invisible became knowable and the impossible became reality. Bohr's model of the atom was not just a scientific theory. It was a vision of order within chaos, a leap of faith across the void of the unknown. It taught humanity that knowledge does not end where mystery begins. It begins there. The year 1913 marked the dawn of a new intellectual age, but for Niels Bohr, it was only the beginning of a lifelong quest to understand nature's hidden logic. His atomic model had offered clarity, yet the deeper he gazed into its mathematics, the more layers of mystery unfolded. To Bohr, each discovery was not an endpoint, but an invitation to ask bolder questions. Why should electrons occupy only specific orbits? Why should energy exist in discrete steps rather than flowing continuously like waves upon a pond? These questions became the pulse of his thinking and the heartbeat of modern physics. Bohr believed that nature, though it might appear strange, was not arbitrary. The quantized orbits were not accidents, they were signatures of harmony at the smallest scales of reality. Each electron, confined to its energy level, followed a rhythm as precise as music, jumping from note to note when energy was exchanged. In this vision, the atom resembled a cosmic orchestra whose instruments were invisible, yet whose melodies filled the universe. The simplicity of the model gave scientists a tool to explore complex phenomena with new precision, yet its implications reached far beyond the laboratory. As Bohr's ideas spread, the scientific world began to awaken to the quantum revolution. Young physicists found themselves drawn to Copenhagen, which soon became a temple of theoretical thought. The discussions there were electric, filled with chalk, dusted blackboards, long debates that stretched late into the night, and the hum of possibility. It was not only the equations that captivated them, but the spirit behind them. Bohr encouraged questions that pierced the surface of science and touched the philosophy of existence itself. He would often pause during a calculation and ask, "What do we really mean by this?" For him, understanding required both logic and imagination. Yet even as his model triumphed, Bohr knew its limits. The idea of electrons orbiting in neat circles was a useful image but not a literal truth. The atom was far more elusive than the human mind could picture. Still, The Bohr model's success in explaining hydrogen's spectrum and predicting experimental results gave it monumental credibility. It became a cornerstone of physics education and inspired generations of researchers. But soon, new evidence began to challenge its boundaries. When scientists examined elements heavier than hydrogen, the spectra became more complex. The simple circular orbits could no longer account for every line or fine structure. Even hydrogen itself, when examined under high precision, displayed subtle deviations that demanded a more sophisticated explanation. This was the moment when theory had to evolve once again, and Bohr, true to his nature, embraced the challenge. He welcomed collaboration with bright young minds like Werner Heisenberg and Wolfgang Pauli, whose fresh perspectives would eventually expand the quantum framework. Meanwhile, Bohr's philosophical reflections deepened. He realized that describing atomic behavior required a new kind of language. Classical words like position, orbit, or path did not truly apply to entities governed by quantum laws. Instead of trying to force the atom into human categories, Bohr sought to adapt human thought to the atom's nature. This intellectual humility became his trademark. He often said that clarity comes not from simplifying reality, but from respecting its complexity. In his eyes, the atom was not just a physical object, but a metaphor for the limits of knowledge. The seeds of this philosophy were already present in the very structure of his atomic model. The quantization of energy represented more than a mathematical constraint. It symbolized the boundaries of what can be known. Between energy levels, there existed no stable states. The electron could not be halfway between orbits. Similarly, in the pursuit of truth, there might be regions where certainty cannot exist, where knowledge must leap like an electron between one insight and another. This poetic dimension gave Bohr's science a rare depth, blending logic with a sense of wonder. As quantum theory matured through the 1920s, Bohr's model evolved into something more abstract yet more accurate. The emergence of quantum mechanics, led by Heisenberg's matrix mechanics and Schrödinger's wave equations, replaced Bohr's circular orbits with probability clouds and mathematical symmetries. Though the visual simplicity of the Bohr atom gave way to complex formalism, the spirit of his idea survived. Every quantum model still carried the echo of his central principle: that energy is discrete, that stability comes from quantization, and that observation itself plays a role in defining reality. For Bohr, this evolution was not a contradiction, but a natural progression. He saw quantum mechanics not as a rejection of his model, but as its completion. The equations of Schrödinger and the uncertainty principle of Heisenberg gave mathematical form to ideas that Bohr had intuitively grasped years earlier. His early picture of electrons in defined orbits had been an educational scaffold, useful until a deeper theory could stand on its own. When that time came, Bohr gladly set aside his old imagery, demonstrating a humility that few pioneers possess. He was not attached to being right, he was devoted to discovering what was true. Bohr's atomic model also had a profound influence on chemistry. By explaining why electrons occupy specific shells, it clarified the periodic behavior of the elements, the mysterious regularity of the periodic table. The reason why certain elements share similar properties now had a quantum foundation. Each row of the table corresponded to the filling of electron shells, and each chemical bond could be understood as an exchange or sharing of electrons between atoms. The invisible architecture of matter suddenly became visible in the language of energy levels and quantum transitions. Chemistry and physics, once separate disciplines, were now joined at the quantum level. This unity of knowledge was one of Bohr's greatest gifts to science. He showed that the world, though divided into disciplines, is governed by universal principles. His model demonstrated that understanding the smallest entity, the atom, could illuminate the vastness of the cosmos. The same laws that guided an electron's motion whispered through the movements of stars and galaxies. For Bohr, this was not coincidence. It was a profound sign that nature's design is consistent, elegant, and interconnected. However, the elegance of theory was shadowed by the practical realities of a changing world. As the 20th century unfolded, the atom's power began to reveal its darker side. The same understanding that explained atomic spectra also opened the door to nuclear fission and the release of unimaginable energy. Bohr, deeply aware of these implications, became both a scientist and a moral voice. During the Second World War, he fled Nazi-occupied Denmark and eventually contributed to the Allied research efforts. But even then, he remained an advocate of transparency and international cooperation. He believed that the discoveries of science should unite humanity, not divide it. Bohr's insights into the atomic nucleus and quantum principles continued to influence nuclear physics, yet he never lost sight of the philosophical questions that had always guided him. In his later years, he developed the principle of complementarity, the idea that objects can exhibit mutually exclusive properties depending on how they are observed. This notion, rooted in his atomic model, became a cornerstone of modern physics and a reflection of his worldview. That truth is often composed of opposites, each revealing a different aspect of reality. Even as the atom's mysteries deepened with the discovery of quantum fields and subatomic particles, scientists continued to look back to Bohr as the pioneer who gave the invisible world its first coherent form. His atomic model, though surpassed in technical detail, remained a symbol of creativity and courage in scientific thought. It reminded researchers that every great advance begins with a leap of imagination, a willingness to see the familiar in an entirely new way. In classrooms and textbooks across the globe, the Bohr atom continues to be drawn, a tiny nucleus encircled by neat rings of electrons. Teachers know it is an oversimplification, yet they still use it because it captures something timeless, the moment when humanity first glimpsed the atom not as a mystery, but as a structure governed by discernible rules. Each line in that simple diagram carries the story of a man who dared to blend the tangible and the abstract, who refused to accept that the unknown must remain unknowable. Bohr's life itself mirrored the balance he found in nature. He was both scientist and philosopher, realist and dreamer. His conversations with Einstein on the meaning of quantum mechanics remain among the most profound dialogues in the history of science. Einstein sought deterministic order, Bohr accepted probabilistic reality. Their debates, though sometimes heated, were acts of mutual respect, two giants grappling with the limits of knowledge. In those exchanges, the spirit of Bohr's atomic model lived on, a quest not for certainty but for understanding. As decades passed, quantum theory advanced into realms Bohr could scarcely have imagined: quantum computing, particle accelerators, and theories of everything. Yet at its heart, the logic of quantized energy levels still governed the behavior of atoms and light. The transitions Bohr described became the foundation for lasers, spectroscopy, and countless modern technologies. Every time a fluorescent bulb glows or a GPS signal relies on atomic clocks, the quiet genius of Bohr's vision flickers into life. But beyond the laboratories and equations, Bohr's atomic model carries a philosophical lesson that continues to resonate. It teaches that nature is not obliged to conform to human expectations. It invites humility, the recognition that the more we learn, the more mysterious the universe becomes. Bohr once remarked that anyone not shocked by quantum theory has not understood it. This statement captures both the wonder and the discomfort that his model introduced. It forced humanity to accept uncertainty as a fundamental feature of existence, not a flaw to be fixed. In the grand narrative of science, Bohr's contribution marks a turning point, the moment when physics became truly modern. His atomic model stands at the crossroads between the deterministic past and the probabilistic future. It represents both the end of classical certainty and the birth of quantum creativity. Through its framework, humanity learned to see the world not as a rigid machine, but as a dynamic interplay of possibilities. Imagine for a moment the world before Bohr. Atoms were mysterious, their behavior inexplicable. The colors of stars, the chemistry of life, the glow of gases, all were unsolved puzzles. Now imagine the world after Bohr light and matter united under one principle, energy levels explaining color and stability, quantum leaps connecting the microscopic with the macroscopic. That transformation is the essence of his legacy. In the quiet corridors of the Niels Bohr Institute today, echoes of his voice still seem to linger. The blackboards that once bore the first equations of the quantum atom have long been erased. But the spirit of inquiry he nurtured endures. Every new discovery in physics, from quantum entanglement to particle symmetries, carries a trace of his influence. The atom, once a symbol of simplicity, remains a source of infinite complexity, and Bohr's name is forever intertwined with its story. His atomic model was not the final truth, but it was the first great truth of the quantum era. It taught scientists how to think differently, how to embrace paradox without fear. It was the moment when humanity's gaze turned inward, into the heart of matter, and found there a reflection of its own curiosity and courage. Niels Bohr's model of the atom was revolutionary not only because it explained what others could not, but because it changed the very meaning of explanation itself. It demonstrated that progress comes from the marriage of evidence and imagination, from the courage to challenge even the most sacred laws when they no longer describe reality. Through his model, Bohr gave us more than a picture of the atom. He gave us a philosophy of inquiry, one that continues to shape every corner of science. As the credits roll on this story of discovery, one can almost hear Bohr's calm voice reminding future generations that knowledge and mystery are not enemies but partners. Each discovery illuminates the darkness, but also deepens it. The atom, once thought to be the smallest and simplest unit, revealed a universe within itself, and in that revelation, Bohr showed humanity something extraordinary, that even in the smallest particle lies an infinite cosmos waiting to be understood. The legacy of Niels Bohr's atomic model is thus not confined to physics alone. It is a story about human perception, creativity, and humility before nature. It tells us that truth is not static, it evolves. It tells us that even the smallest leap of imagination can transform the world. And above all, it tells us that the atom, that invisible building block of everything, is not just matter, but a mirror reflecting the boundless curiosity of the human spirit. In the unfolding saga of 20th century physics, there exists a chapter unlike any other, a dialogue between two of humanity's greatest minds, Niels Bohr and Albert Einstein. It was not merely a scientific exchange, it was a battle of philosophies, a clash of worldviews, and a testament to the power of respectful disagreement. Between these two giants, the nature of reality itself became the subject of debate. They stood at the crossroads of classical certainty and quantum ambiguity, gazing into the same mysteries, yet seeing them through different lenses. Together they shaped the intellectual destiny of modern science. When Niels Bohr first met Albert Einstein, the world was in the midst of revolutionary change. Einstein had already transformed physics with his theory of relativity, revealing that space and time were intertwined, and that energy and matter were two faces of the same coin. Bohr, meanwhile, had just introduced his model of the atom, a bold new idea that brought quantum principles into the heart of matter. They admired one another deeply, recognizing in each other the same devotion to truth, yet from their first encounters, it was clear that their philosophies would diverge. Einstein sought order, precision, and determinism. Bohr accepted uncertainty, probability, and paradox. Their friendship began in mutual respect. Both men valued deep thought more than public recognition, and both were driven by an unrelenting curiosity about nature's secrets. Einstein saw in Bohr a kindred spirit, someone capable of grasping the profound philosophical implications of physics. Bohr, for his part, regarded Einstein as the greatest mind alive, the man who had redefined space and time. In the early 1920s, their paths crossed frequently at scientific conferences and private gatherings. These meetings soon became legendary for the intensity of their discussions. Einstein's discomfort with the emerging quantum theory was not born of ignorance but of intuition. He had helped lay its very foundations, introducing the idea of the photon and quantized energy. Yet as quantum mechanics developed under Bohr's guidance, it began to depart from the deterministic framework Einstein held dear. The new theory suggested that at the smallest scales, nature behaved not with strict causality, but with inherent randomness. Events could only be predicted in terms of probabilities. For Einstein, this was intolerable. To him, the universe was a grand design of order, not a game of chance. His famous words, "God does not play dice with the universe," captured his unease. Bohr, on the other hand, saw in quantum uncertainty not chaos but a deeper kind of harmony. To him, the apparent randomness of subatomic events did not mean that nature lacked order. It meant that the old classical definitions of order no longer applied. The observer and the observed could no longer be separated. The act of measurement influenced the outcome. For Bohr, this was not a flaw in nature, but a revelation about the limits of human understanding. He would often respond to Einstein's objections with calm conviction. "Einstein, stop telling God what to do." Their debates reached their height at the Solvay conferences in Brussels, gatherings that brought together the most brilliant physicists of the time: Planck, Schrödinger, Heisenberg, Pauli, Dirac, and many others. It was at these meetings, especially those held in 1927 and 1930, that Bohr and Einstein engaged in some of the most famous intellectual duels in history. The atmosphere was charged with tension and excitement. On one side stood Einstein, determined to expose the weaknesses of the new quantum theory. On the other stood Bohr, defending the strange but consistent results of the quantum framework. Einstein's strategy was ingenious. He presented thought experiments, mental challenges designed to reveal contradictions in quantum mechanics. In one, he proposed a box filled with radiation, equipped with a clock-controlled shutter. By measuring the energy of a photon released from the box, one could, in principle, determine both its energy and emission time precisely, something forbidden by Heisenberg's uncertainty principle. If Einstein's argument held, it would mean that quantum mechanics was incomplete, missing hidden variables that restored determinism. Bohr, however, responded with equal brilliance. After hours of contemplation, he found the flaw in Einstein's reasoning. He invoked the general theory of relativity itself, Einstein's own creation, to show that measuring the box's mass with such precision would affect its gravitational potential, introducing uncertainty in time measurement. In other words, even in Einstein's own universe, nature preserved the uncertainty principle. Einstein smiled, acknowledging defeat with characteristic grace, though he was never fully convinced. Bohr later recalled that these debates were not battles to destroy, but dialogues to deepen understanding. The dynamic between the two men was a delicate balance of admiration and opposition. Einstein respected Bohr's intellect, but he could not accept the Copenhagen interpretation, Bohr's assertion that physical reality exists only when observed. To Einstein, reality was independent of observation. The moon, he said, exists even when no one looks at it. Bohr replied that quantum mechanics does not deny the existence of reality, only that we cannot speak meaningfully of its properties without reference to measurement. To Bohr, physics was not about describing what is, but what can be known. These exchanges went far beyond equations. They touched the very philosophy of science. Bohr believed that the role of physics was to create a language for describing phenomena, not to claim ultimate truths. Einstein sought an objective reality underlying all appearances. Their disagreement reflected two contrasting visions of knowledge itself, one grounded in certainty, the other in acceptance of limits. Neither man was wrong. They simply stood on opposite sides of a philosophical divide that continues to shape science today. Despite their differences, their debates were conducted with deep mutual respect. Witnesses at the Solvay conferences often recalled how, after intense discussions, the two would share quiet walks or late-night conversations, each pondering the other's words. Bohr admired Einstein's moral and intellectual integrity, and Einstein in turn respected Bohr's humility and depth. They were not enemies but intellectual companions, navigating the frontiers of thought. Each needed the other to refine his own understanding. As the years passed, their debates evolved into correspondence and occasional visits. Einstein continued to challenge quantum theory, seeking a more complete explanation. In 1935, along with Podolsky and Rosen, he published the famous EPR paper, a thought experiment designed to show that quantum mechanics was incomplete. The paper introduced the idea of entanglement, suggesting that two particles could be correlated in ways that allowed instant influence across space. Einstein found this spooky action at a distance unacceptable. It violated his sense of locality and causality. Bohr, however, responded with characteristic insight, arguing that the EPR paradox only reinforced the necessity of complementarity, that reality could not be fully described without considering the whole experimental context. Their exchange over the EPR paradox became one of the most profound dialogues in scientific history. Einstein's challenge would later inspire decades of research, leading to the development of quantum information theory and experiments that tested Bell's inequalities. Ironically, it was Einstein's own critique that eventually confirmed the completeness of Bohr's quantum view. Yet Bohr never gloated. To him, Einstein's challenges were gifts, opportunities to clarify and deepen the meaning of quantum mechanics. He once remarked that every time Einstein threw him a paradox, he felt as though he had been handed a pearl of wisdom. Polished by the friction of thought, the relationship between Bohr and Einstein transcended science. It was a dialogue about how humans perceive the universe, whether the cosmos is a machine governed by unbroken law or a web of possibilities shaped by observation. Their debates captured the tension between logic and mystery, between the desire for certainty and the acceptance of ambiguity. In many ways, they reflected the broader struggles of the 20th century, a century in which humanity discovered both the boundless power of knowledge and the moral responsibility that comes with it. As the world moved into darker times, with wars and political upheavals, both men found themselves drawn to questions beyond physics. Einstein became a passionate advocate for peace and human rights, while Bohr turned his attention to the ethical responsibilities of science, especially after the development of nuclear weapons. Despite the heavy burdens of their age, their respect for each other endured. In 1947, when Bohr visited Princeton to see Einstein, the two old friends sat together, reminiscing and reflecting. Though they never reached agreement on quantum mechanics, they shared a quiet understanding that their debate had enriched science far more than any single theory could have. Bohr often said that Einstein's challenges kept him honest, forcing him to test every assumption. Einstein, for his part, acknowledged that though he could not accept quantum indeterminacy, he admired Bohr's courage to embrace it. In their lifelong dialogue, truth was not a destination but a journey, a process of refinement through disagreement. Their exchanges were not about victory, but about progress. They demonstrated that science advances not only through discovery, but through dialogue, not only by solving problems, but by asking the right questions. To watch Bohr and Einstein debate was to witness the human mind at its most profound. Their words carried the weight of centuries of inquiry, yet their tone was often light, even humorous. They understood that the universe was not easily tamed, and that humility before nature was the beginning of wisdom. In their encounters, the very spirit of scientific inquiry came alive, restless, curious, and eternally questioning. When Bohr looked back on those debates in his later years, he described them not as conflicts but as conversations between two ways of seeing the world. He saw Einstein as a guardian of continuity, a defender of reason, while he himself represented the acceptance of nature's strangeness. Together, they balanced the scale of knowledge. Without Einstein, Bohr's ideas might have grown unchallenged and rigid. Without Bohr, Einstein's vision might have remained rooted in an outdated certainty. Their opposition was not a divide but a dynamic, the very heartbeat of science itself. By the time Einstein passed away in 1955, Bohr felt a deep sense of loss, not only of a friend but of a mirror against which he had tested his own understanding for decades. He wrote with profound affection, calling Einstein's lifelong search for truth an inspiration to all who seek understanding. Though their interpretations differed, both men shared an unwavering faith in the rational beauty of the universe. As we look back today, the Bohr-Einstein debates stand as milestones in human thought. They remind us that progress is not born from agreement, but from challenge. Their conversation continues in every laboratory and classroom where students wrestle with the meaning of quantum theory. The echoes of their voices still resonate whenever we ask whether reality exists independent of observation, or whether nature itself is woven from probabilities. Their collaboration and debate were not mere episodes in scientific history. They were expressions of humanity's eternal dialogue with the unknown. Bohr and Einstein embodied two complementary aspects of the human spirit: the yearning for certainty and the courage to embrace mystery. Together, they transformed not just physics but the philosophy of knowledge itself. And so, as we revisit their story, we find that the true power of their exchange lies not in who was right or wrong, but in how they taught the world to think. They showed that even the deepest disagreements, when pursued with respect and curiosity, can become engines of enlightenment. Their friendship, forged in the fires of debate, remains one of the most inspiring relationships in the history of science, a testament to the fact that in seeking to understand the universe, we also come to understand ourselves. As the 1920s unfolded, the world of physics transformed into an arena of deep philosophical reflection and profound intellectual struggle. At the heart of this transformation stood Niels Bohr and Albert Einstein, two titans whose ideas would define not just the course of science, but the very way humanity perceived truth, reality, and existence itself. Their debates were not merely academic disputes, they were battles between two worldviews, each grounded in reason yet divided by belief. Bohr, with his quiet determination and deep philosophical insight, believed in a universe governed by probabilities, a world where observation shaped reality. Einstein, guided by his conviction in order and determinism, held fast to the belief that nature followed precise laws, independent of human observation. Together, they created a dialogue that stretched the boundaries of human thought. Einstein had been one of the first to challenge classical physics with his theory of relativity, showing that time and space were not absolute but interconnected dimensions of the universe. Yet when quantum mechanics began to take shape, he found himself troubled by its implications. The notion that particles could exist in multiple states at once, or that their properties could remain uncertain until measured, was something Einstein could not accept. "God does not play dice with the universe," he famously said, expressing his discomfort with randomness in nature. Bohr, however, found beauty in this uncertainty. He saw the quantum world not as chaotic, but as deeply ordered in its own mysterious way, an order that revealed itself only through probability, not certainty. Their intellectual duel reached its peak during the Solvay conferences in Brussels, gatherings of the world's greatest physicists. In these sessions, filled with smoke, chalk dust, and restless minds, the two men exchanged arguments that would echo across decades. Einstein would propose thought experiments designed to expose what he believed were flaws in quantum theory. Bohr, meticulous and patient, would respond by analyzing every detail, often revealing that Einstein's arguments reinforced rather than disproved the strange logic of quantum mechanics. Their exchanges were sharp but respectful, filled with mutual admiration and an underlying recognition of each other's genius. It was science elevated to philosophy and philosophy grounded in mathematics. At one conference, Einstein presented a scenario involving a photon and a slit, a thought experiment designed to test whether the uncertainty principle could truly hold under precise measurement. Bohr, after a night of deep contemplation, returned with an answer so subtle and profound that it silenced even Einstein. He showed that Einstein's own theory of relativity ensured the validity of uncertainty, meaning that the two seemingly opposing frameworks, relativity and quantum mechanics, were more intertwined than anyone had imagined. That moment symbolized not a victory for one man over another, but a realization of how vast and interconnected the universe truly was. Bohr and Einstein, through their intellectual confrontation, were carving out the foundation of modern physics. Outside the debates, Bohr and Einstein shared a mutual respect that transcended disagreement. They corresponded frequently, their letters filled with warmth, curiosity, and philosophical depth. Bohr admired Einstein's courage to challenge every idea, while Einstein respected Bohr's humility before nature's mysteries. For Bohr, Einstein's questions were a gift. They forced him and his colleagues to sharpen their understanding of quantum theory, to test its boundaries, and to refine its interpretations. In many ways, Einstein became the most valuable critic of Bohr's ideas, and Bohr became the quiet philosopher who pushed Einstein to confront the limits of classical logic. Bohr's perspective was deeply influenced by his philosophical approach to science. He believed that human language and thought were limited tools when describing the atomic world. The phenomena of quantum mechanics, he argued, could not be fully expressed in traditional terms. Instead, one had to accept complementarity, the idea that nature can exhibit different, even contradictory, aspects depending on how it is observed. Light, for example, could behave as both a wave and a particle, but never both at once. This concept became a cornerstone of Bohr's philosophy and a key to understanding the dual nature of reality. Einstein found this idea unsettling. For him, nature's laws should exist independently of human observation. Bohr, however, believed that observation was not a disturbance, but an essential part of the fabric of reality itself. Their debates rippled through the scientific community. Young physicists like Werner Heisenberg, Erwin Schrödinger, and Wolfgang Pauli looked on with awe, inspired by the intellectual fire exchanged between their mentors. It was through these discussions that quantum mechanics gained its philosophical backbone. Einstein's insistence on realism forced Bohr and others to clarify their interpretations, while Bohr's patient reasoning ensured that the probabilistic view of the universe became an accepted foundation of modern physics. Even when Einstein later collaborated with Podolsky and Rosen to publish the famous EPR paper, arguing that quantum mechanics was incomplete, Bohr responded with his own defense, affirming that completeness lay not in determinism, but in the harmony of probabilities and measurement. These debates did not end with their lifetimes. Instead, they continued to inspire generations of scientists and philosophers. Decades later, experimental physicists would revisit Einstein's arguments through advanced tests of quantum entanglement, experiments that seemed to confirm Bohr's probabilistic worldview. Yet even then, the questions remained open, profound, and endlessly fascinating. What is reality? Does the universe exist independently of observation? Is there truly randomness at the heart of nature, or is there a deeper order still beyond human reach? These are the questions that Bohr and Einstein left behind, not as answers, but as eternal invitations to wonder. Their philosophical differences also reflected their personalities. Einstein, ever the idealist, sought a universe of elegance and mathematical perfection, one that could be described through unified laws. Bohr, more pragmatic and introspective, saw beauty in paradox and complexity. He once said, "The opposite of a profound truth may well be another profound truth." For Bohr, truth was not singular but layered, changing with perspective. Einstein could not accept such relativism in the fabric of reality, yet he admired Bohr's courage to embrace uncertainty with such grace. Together, they personified the dual nature of science itself: reason and imagination, logic and wonder, order and mystery. Beyond science, their debates touched the very essence of human thought. They revealed how the search for knowledge is never linear, but filled with contradictions that must be reconciled through humility and creativity. Einstein's challenge, that God does not play dice, was more than a rejection of quantum uncertainty. It was a plea for coherence in a universe that often defied human logic. Bohr's calm reply, "Stop telling God what to do," was not defiance but acceptance, an acknowledgement that the universe may be far stranger and more subtle than we can imagine. This exchange captured the essence of their philosophical divide, a divide that continues to shape how scientists think about reality today. In their later years, both men reflected on the journey they had shared. The Second World War had changed everything, not only science but humanity itself. Bohr, deeply involved in nuclear research, became a voice for peace and ethical responsibility in science. Einstein, from his exile in America, echoed the same concerns, warning about the dangers of unchecked scientific power. Though their views on quantum mechanics never fully converged, their moral convictions aligned. They both saw science as a human endeavor that must be guided by conscience as much as curiosity. Bohr often said that the purpose of science was not to conquer nature, but to understand it, and Einstein, despite their differences, shared that belief in his heart. By the time the two great minds passed away, they had changed not only physics, but the way humanity approached truth itself. Their debates were more than intellectual exercises. They were dialogues about the limits of human knowledge, the nature of existence, and the meaning of discovery. The Bohr-Einstein debates showed that disagreement can be the most powerful engine of progress. That through dialogue, humility, and persistence, science can rise above ideology and emotion to glimpse the structure of reality itself. Today, when scientists manipulate quantum bits, explore entanglement, or dream of unifying relativity and quantum mechanics, they are walking in the footsteps of Bohr and Einstein. Every experiment testing the boundaries of uncertainty, every philosophical discussion about the observer and the observed, carries the echo of their voices. Bohr's insistence that nature cannot be separated from measurement continues to influence quantum theory, while Einstein's quest for deterministic beauty fuels the ongoing search for a unified theory of everything. Their intellectual legacy is not a conclusion but a continuum, an endless conversation between order and chance, determinism and uncertainty. In the quiet moments of reflection, one might imagine Bohr and Einstein still in conversation, somewhere beyond time. Bohr, calm and contemplative, explaining that understanding comes not from control but from acceptance. Einstein, passionate and idealistic, insisting that beneath the apparent chaos lies a deeper harmony waiting to be revealed. Together, they represent the two halves of human curiosity, the desire to know and the wisdom to wonder. Their debates remind us that science is not about certainty, but about the courage to question, to explore, and to accept the mysteries that define existence. The story of Bohr and Einstein's collaboration and debates is, in essence, the story of modern physics itself. It is the story of how reason met imagination, how philosophy intertwined with mathematics, and how two men, through disagreement, created a vision of the universe more profound than either could have achieved alone. They showed that truth is not found in isolation but in dialogue, not in victory but in understanding. And as long as humanity seeks to unravel the secrets of the cosmos, the voices of Niels Bohr and Albert Einstein will continue to guide the way, whispering through every atom, every wave, and every question that dares to ask, "What is reality?" In the closing years of the 19th century, physics appeared complete. The great pillars of Newton's mechanics, Maxwell's electromagnetism, and thermodynamics seemed to explain everything from the motion of planets to the glow of stars. Many scientists believed that all that remained was to refine measurements to greater precision. Yet, beneath this apparent perfection, cracks had begun to form, subtle, strange discrepancies that refused to be explained by classical laws. The spectrum of light emitted by atoms, the mysterious photoelectric effect, and the behavior of energy in blackbody radiation, all pointed toward something deeper, something hidden in the very fabric of reality. It was in this period of confusion that Niels Bohr emerged, bringing with him a new way of seeing the unseen, and unknowingly setting the stage for the birth of quantum mechanics. Bohr's journey began not with grand theories, but with questions. What held electrons in place? Why didn't they simply spiral into the nucleus as classical physics predicted? What governed the stability of matter itself? At a time when atoms were little more than abstract ideas, Bohr's curiosity was revolutionary. In 1913, while working in England under Ernest Rutherford, he encountered Rutherford's nuclear model of the atom, a dense, positively charged core surrounded by orbiting electrons. The model was elegant, but unstable under classical physics. According to Maxwell's equations, a moving electron should radiate energy continuously, causing it to lose momentum and collapse into the nucleus within a fraction of a second. Yet matter existed. Atoms endured. Clearly, something fundamental was missing. Bohr dared to imagine that the laws governing the tiny world of the atom were not the same as those ruling planets and stars. Drawing inspiration from Max Planck's idea that energy is quantized, that it comes in discrete packets rather than continuous waves, Bohr proposed a radical solution. He suggested that electrons could orbit the nucleus only in specific, quantized energy levels, and that they could move between these levels only by absorbing or emitting precise amounts of energy, known as quanta. This simple but profound idea broke from every known principle of classical physics. It introduced a new language for describing nature, one that spoke in probabilities and jumps rather than certainties and continuities. When Bohr published his atomic model in 1913, the scientific world was astonished. His theory not only explained the stability of atoms, but also accounted for the mysterious spectral lines of hydrogen. Those bright, colorful patterns observed when atoms emit light. Each line corresponded to a transition between two energy levels in the atom, and Bohr's formula predicted their exact positions with breathtaking accuracy. Suddenly, the strange and beautiful patterns of atomic spectra were no longer random. They were signatures of an underlying quantum order. The invisible world of the atom had found its first coherent description. Bohr's model was more than a theory. It was a bridge between two worlds. It linked the continuous, deterministic realm of classical physics with the discrete, probabilistic world that would become quantum mechanics. For the first time, scientists glimpsed the possibility that the universe operated on two levels of reality, one that we could see and another hidden beneath, governed by principles that defied intuition. The concept of quantization, the idea that energy and motion come in discrete steps, became the cornerstone upon which an entirely new physics would be built. Bohr's bold proposal did not go unchallenged. Many of his contemporaries, including some of the greatest minds of the time, found his ideas difficult to accept. How could electrons jump between orbits without passing through the space in between? What did it mean for energy to be emitted or absorbed in quanta? Even Bohr himself was troubled by the implications. He was not offering an answer so much as a new way of thinking, a framework that could describe what experiments revealed, even if it could not yet explain why nature behaved that way. This humility, this willingness to let go of certainty, became Bohr's greatest strength and the seed of quantum theory itself. As the years progressed, Bohr's ideas inspired a generation of young physicists who would go on to reshape science forever. Werner Heisenberg, a brilliant student from Germany, took Bohr's quantized energy levels and transformed them into a mathematical structure, matrix mechanics, that described atomic behavior without relying on visual orbits. Erwin Schrödinger, working independently, developed wave mechanics, introducing the famous Schrödinger equation that treated electrons as waves rather than particles. At first, these two approaches seemed incompatible, but under Bohr's philosophical guidance, they were understood as two complementary views of the same reality, a concept that became central to his Copenhagen interpretation. Bohr's influence extended far beyond equations. He provided the intellectual and emotional foundation for what would become quantum mechanics, a framework that abandoned the rigid determinism of the past in favor of a probabilistic view of nature. The atom was no longer a miniature solar system, as imagined by Rutherford, but a dynamic, uncertain world of probabilities and potentials. In Bohr's vision, the act of measurement itself became part of reality, shaping the outcome of what was observed. This was not just a new theory, it was a new philosophy of existence. The creation of quantum mechanics was not an overnight revolution, but a gradual awakening. Step by step, experiment by experiment, nature revealed her quantum character. The photoelectric effect, explained by Einstein in 1905, had already hinted that light behaved like a stream of particles, or photons. Planck had shown that energy exchanges occurred in discrete amounts, but it was Bohr who took these isolated ideas and built them into a coherent picture of atomic structure. His model provided the missing link between the behavior of radiation and the behavior of matter. It unified the strange observations into a single vision, a vision that would soon evolve into the complete framework of quantum mechanics. By the mid-1920s, Bohr's Institute in Copenhagen had become the epicenter of this revolution. Young physicists from across Europe flocked there to discuss, debate, and dream. The building pulsed with intellectual energy. Ideas collided like atoms, releasing bursts of insight that illuminated the path forward. Bohr was not merely a teacher, he was a guide who encouraged open dialogue and philosophical reflection. He often told his students that understanding required not just logic, but imagination, the courage to see beyond the limits of common sense. It was in this environment that the principles of quantum mechanics were shaped, tested, and refined. The beauty of Bohr's vision lay in its balance between theory and humility. He never claimed to have unlocked the final secrets of the atom. Instead, he believed that every discovery opened new questions. When asked how electrons decide which orbit to occupy or how they know when to jump, Bohr would smile and remind his students that nature does not reveal her mechanisms easily. What mattered, he said, was not the path of the electron, but the results we can observe. In this simple statement lay the philosophical heart of quantum mechanics, that knowledge itself is limited, that the act of observation defines the boundaries of what can be known. As Bohr's atomic model spread, its success inspired both awe and unease. It challenged the very foundations of scientific thinking. For centuries, physics had been built on the assumption that the universe was a predictable machine. If one knew the initial conditions and the laws of motion, one could, in principle, predict everything. Bohr's model shattered that illusion. In the quantum world, prediction became probability, and certainty gave way to possibility. The universe was no longer a clockwork mechanism, but a dance of chance and order, a symphony of probabilities guided by unseen laws. This shift in perspective was not easy for many to accept. Classical physicists, trained to think in terms of definite causes and effects, struggled to grasp a world where observation itself altered reality. But for Bohr, this was not a flaw, it was a profound truth about existence. He believed that nature was not simply waiting to be discovered. It was participatory, engaging with the observer in ways that blurred the line between subject and object. This philosophical insight would later become one of the defining features of quantum theory, influencing not only physics but also philosophy, psychology, and even art. By 1925, the scientific community stood at a turning point. The old world of certainty had faded, and in its place arose a new world, one defined by waves, quanta, and probabilities. Bohr's pioneering ideas had laid the foundation, but now others were building upon it. Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's elegant mathematics, all these were natural extensions of Bohr's original insight that energy is discrete, that the atom is quantized. Without Bohr's leap of faith, without his willingness to imagine a world beyond classical intuition, the birth of quantum mechanics might never have occurred. And yet, Bohr himself remained cautious. He saw in these developments not a triumph of human mastery, but a deepening of mystery. The more scientists uncovered about the atomic world, the more questions arose about the nature of reality itself. What did it mean for something to exist before it was observed? Could a particle truly be in two states at once? These questions were not merely scientific, they were philosophical, even spiritual. Bohr understood that quantum mechanics was not just a theory of matter, but a mirror reflecting the limits of human knowledge. As Part A draws to its midpoint, the story of Bohr's contribution to the birth of quantum mechanics stands as both a scientific and human triumph. It is the story of how one man's courage to think differently opened a door to a universe stranger and more beautiful than anyone had imagined. His atomic model was more than an explanation. It was a revelation. It taught humanity that the laws of the universe are not fixed, that certainty is an illusion, and that truth, like light, comes in quanta. Bohr's revolutionary vision did not end with the atom. It transformed the entire landscape of science. It showed that progress begins not with answers, but with the humility to ask better questions. And in doing so, Niels Bohr became not just the architect of the quantum atom, but the father of a new way of seeing reality itself. As the quantum revolution gained momentum, Niels Bohr's atomic model became the foundation upon which an entirely new vision of the universe was built. The 1920s were an era of extraordinary transformation, not only in science but in the human understanding of reality itself. Bohr's ideas had opened a doorway into a world that defied common sense, a world where particles behaved like waves, where certainty dissolved into probability, and where observation seemed to shape the very fabric of existence. From this doorway emerged the full birth of quantum mechanics, a theory that would redefine knowledge, challenge philosophy, and forever alter the course of human thought. Bohr's 1913 atomic model had explained hydrogen beautifully, but as scientists began to explore more complex atoms, new puzzles arose. The simplicity of Bohr's circular orbits could not fully account for the intricate spectra of multi-electron atoms or the fine details seen in experiments. Yet, Bohr's core insight, that energy levels are quantized, remained unshaken. His model was the first light in a vast unknown landscape, and others were now joining him to chart it. Among them were brilliant young minds who had been inspired by Bohr's daring vision. Men like Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger, who would each carry the quantum torch forward in their own way. Heisenberg, one of Bohr's most gifted protégés, took the leap from visual imagery to pure mathematics. He realized that trying to picture electrons as tiny planets orbiting a nucleus was misleading. The atom was not a miniature solar system. It was a dynamic field of possibilities. Instead of tracking where electrons were, Heisenberg focused on what could be measured: their energy transitions, their frequencies, their intensities. Out of this radical approach emerged matrix mechanics, a new mathematical framework that described the behavior of atoms without relying on visual models. This was quantum theory in its purest form, abstract, symbolic, and astonishingly accurate. When Heisenberg presented his findings to Bohr, the older physicist immediately recognized their importance. Though complex, Heisenberg's method captured the spirit of Bohr's quantized energy concept, taking it to a new level of precision. Bohr's philosophical openness allowed such bold ideas to flourish. He created an environment in Copenhagen where creativity and deep questioning were encouraged, where no idea was too strange if it helped illuminate the hidden workings of the atom. This spirit of inquiry transformed Bohr's Institute into the beating heart of the quantum world, a sanctuary for those willing to challenge convention and explore the unknown. Almost simultaneously, across Europe, Erwin Schrödinger was approaching the same mysteries from a different direction. Troubled by the abstract nature of matrix mechanics, Schrödinger sought a more visual, continuous description of the atom. Inspired by de Broglie's suggestion that particles could behave like waves, he developed wave mechanics, proposing that electrons were not tiny points but standing waves spread throughout space. His mathematical formulation, known as the Schrödinger equation, described how these waves evolved and interacted. When applied to hydrogen, the results matched Bohr's energy levels perfectly. Two seemingly different pictures, Heisenberg's matrices and Schrödinger's waves, were describing the same underlying truth. Bohr saw in this convergence a profound philosophical meaning. To him, the wave and particle descriptions were not contradictions, but complementary aspects of the same reality. Depending on how an experiment was designed, nature would reveal one face or the other, but never both at once. This insight became one of Bohr's greatest contributions, the principle of complementarity. It taught that our knowledge of the quantum world is fundamentally limited by the conditions of observation. We cannot know the full nature of an electron, we can only know how it behaves when we choose to measure it in a particular way. In Bohr's words, we are not merely spectators, we are participants in the drama of existence. This was the true birth of quantum mechanics, not merely as a mathematical theory, but as a new philosophy of nature. Bohr's interpretation gave meaning to the equations that Heisenberg and Schrödinger had created. It explained why quantum mechanics, despite its apparent contradictions, worked so perfectly. The universe was no longer deterministic but probabilistic, not mechanical, but relational. The act of observation had become inseparable from the observed phenomenon. This was a radical departure from centuries of scientific thinking, yet it resonated deeply with the mysterious behavior of the atomic world. In Copenhagen, discussions on these ideas would often stretch late into the night. Physicists from around the world gathered in Bohr's living room, scribbling equations on scraps of paper, arguing, laughing, and occasionally falling into silent awe at the mysteries they were uncovering. Bohr would listen patiently, sometimes pacing, sometimes pausing for long moments before speaking. His words were often slow and reflective, but when they came, they carried a philosophical depth that transcended science. He encouraged his students not to seek final answers, but to embrace ambiguity as a path to deeper understanding. Under his mentorship, the new generation of physicists learned that uncertainty was not a weakness in knowledge. It was a fundamental feature of nature itself. The realization that uncertainty was intrinsic to reality reached its climax in 1927, when Heisenberg formulated the uncertainty principle, the idea that one cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This principle did not arise from experimental limitations, but from the nature of the quantum world itself. Bohr immediately grasped its significance. It confirmed his belief that the atomic realm could not be described in classical terms. Measurement did not simply reveal what already existed, it created the conditions under which something could exist. The act of observing changed the thing being observed. When Bohr presented these ideas at the Solvay conference in 1927, he faced one of his greatest intellectual challenges, defending the strange new quantum theory against the skepticism of Albert Einstein. Einstein, though one of the founding fathers of quantum physics, could not accept its probabilistic nature. He argued that the theory was incomplete, that there must be hidden variables underlying the apparent randomness. But Bohr stood firm. He believed that quantum mechanics, as it stood, was complete, not because it explained everything, but because it defined the limits of what could be known. Their debates became legendary, echoing through the halls of science for decades. Bohr's ability to bridge the gap between experiment and philosophy made him unique among his peers. He did not view science as a conquest over nature, but as a dialogue with it. Every measurement, every equation, was a question asked to the universe, and nature responded in her own cryptic, poetic way. He often reminded his students that clarity in physics was not the elimination of mystery, but the ability to live with it gracefully. The atom, he would say, was a teacher that revealed not only the structure of matter, but the structure of human thought itself. As the quantum framework solidified, its implications began to ripple outward, influencing other fields of science. Chemistry, once governed by the laws of classical mechanics, was reimagined through quantum principles. The periodic table, previously a pattern without explanation, now made sense as the manifestation of quantized electron shells. The stability of molecules, the bonding of atoms, even the color of substances, all could be traced back to the rules Bohr had helped define. Quantum mechanics also began to illuminate phenomena far beyond the laboratory: the behavior of stars, the fusion powering the sun, and the subtle dance of particles within the nucleus. For Bohr, these successes were both exhilarating and humbling. He saw in them a reflection of the human journey toward understanding, a journey marked by bold leaps and constant reevaluation. The birth of quantum mechanics was not merely the discovery of a new theory. It was the awakening of a new mindset. Humanity had learned that the universe was not built upon certainty, but upon interaction, not upon predictability, but upon relationship. Bohr's ideas had redefined the boundaries between observer and observed, between knowledge and mystery. By the 1930s, the principles born from Bohr's insights had matured into a full-fledged theory that governed the microscopic world with astonishing accuracy. Quantum mechanics became the language of modern physics, unlocking technologies that would shape the future: semiconductors, lasers, nuclear energy, and eventually, the computers and communication systems of the modern age. Bohr's intellectual descendants carried his vision forward, translating his philosophical depth into practical innovation. Yet Bohr himself remained ever the philosopher, scientist, warning that with great understanding comes great responsibility. He believed that the power revealed by quantum mechanics was a double-edged sword. It offered humanity unprecedented knowledge and control, but also the potential for destruction. The discovery of the atom's inner workings inevitably led to the development of nuclear weapons, a consequence Bohr deeply regretted. He urged for openness and cooperation among nations, believing that the secrets of nature should unite humanity, not divide it. In his later years, Bohr became not just a physicist, but a moral voice for the scientific community, reminding the world that understanding reality must go hand in hand with wisdom and compassion. Looking back on his life's work, Bohr saw quantum mechanics as more than a scientific triumph. It was, in his eyes, a reflection of the human condition itself, a reminder that truth is multifaceted, that knowledge is shaped by perspective, and that uncertainty is not chaos, but the essence of creation. His philosophy of complementarity extended beyond physics, influencing psychology, art, and even theology. It suggested that reality could be understood only by accepting opposing truths, that light and darkness, order and chance, knowledge and mystery, were not contradictions, but partners in the dance of existence. In the quiet twilight of his career, Bohr often reflected on the journey that had begun with a simple question about the structure of the atom. That question had unfolded into a revolution that reshaped the world. From the quantized orbits of hydrogen to the probabilistic waves of quantum mechanics, his ideas had transcended their origins to become the foundation of modern science. Yet Bohr never saw himself as a conqueror of knowledge. He saw himself as a humble participant in nature's grand experiment, a thinker guided by curiosity and wonder. The birth of quantum mechanics through Bohr's ideas was not just the story of one man's discovery. It was the story of humanity learning to see the universe anew, to let go of the need for certainty, and embrace the profound beauty of the unknown. Bohr's vision taught that truth lies not in simplicity or predictability, but in the interplay of opposites. His legacy endures in every quantum equation, every photon experiment, every whisper of uncertainty that echoes through the cosmos. In the end, Niels Bohr gave humanity more than a model of the atom. He gave it a model of thought. He showed that progress begins where comfort ends, that wisdom arises from doubt, and that reality, in its deepest essence, is a mystery to be experienced rather than conquered. Through his ideas, the quantum world was born, a world that forever changed the meaning of knowledge, the limits of science, and the destiny of human understanding. The story of Niels Bohr's role in the Copenhagen interpretation begins in an era when the very foundations of science were trembling. The early 20th century had already shattered long-held assumptions about space, time, and energy. Now, with the birth of quantum mechanics, the smallest building blocks of nature appeared to defy reason itself. Out of this uncertainty rose a new vision of reality, one that questioned what it even meant to know something. And at the heart of that vision stood Bohr, the quiet Danish physicist who transformed confusion into philosophy and chaos into understanding. To Bohr, quantum mechanics was not merely a set of equations, but a message from nature itself. He realized that the strangeness of the quantum world, where particles behaved like waves and observation seemed to shape reality, was not a flaw in our knowledge but a truth about existence. The Copenhagen interpretation, born in long nights of debate at his institute, became the philosophical framework that gave meaning to the new physics. It taught that we could no longer speak of an objective world independent of observation. Instead, reality at the atomic level was something that came into being only through interaction. When the observer and the observed met in an act of measurement. In Bohr's view, an electron did not have a definite position or momentum until it was measured. It existed only as a wave of probabilities, a cloud of potential outcomes. When an experiment was performed, the wave collapsed into one concrete result. This idea disturbed many, especially Albert Einstein, who believed in an orderly universe where everything had a reason. God does not play dice, Einstein declared, but Bohr calmly replied, "It is not for us to tell God how to play." To Bohr, the universe was not a clockwork machine but a conversation, where every question shaped the answer that nature gave. The Copenhagen interpretation rested on Bohr's principle of complementarity, the idea that contradictory descriptions, like particle and wave, could both be true, depending on how one chose to observe. He believed that nature revealed different aspects of itself under different conditions, and that these aspects, while mutually exclusive, were both essential for a complete understanding. This was not just a theory about atoms. It was a new way of thinking about knowledge itself. It demanded humility, the acceptance that our human language and logic could never fully capture the depth of reality. Bohr's institute in Copenhagen became the center of this revolution. Young physicists from all over the world came to work and argue in his home, often late into the night. The air was charged with energy, the birth of a new philosophy hidden inside mathematical formulas. Heisenberg, Pauli, Born, and many others debated what the equations truly meant. Bohr would listen in silence, sometimes pacing the floor, sometimes speaking in slow, careful words that carried profound insight. His role was not to dominate the discussion, but to guide it, to help others see that the paradoxes of quantum theory were not barriers, but windows into a deeper truth. The Copenhagen interpretation was not just a scientific explanation, it was a reflection of Bohr's worldview. He saw knowledge as something relational, shaped by perspective, context, and the limits of human understanding. In the quantum world, the observer could not stand apart from what was being observed. Every measurement changed the system. This realization blurred the boundary between subject and object, between mind and matter. It was a concept both beautiful and unsettling, for it placed human consciousness, the act of observing, at the center of physical reality. Though Bohr's interpretation became the dominant view in quantum mechanics, it never went unchallenged. Einstein continued to argue that it left too much to chance, that reality must exist independently of observation. Their debates, filled with passion and respect, became the most famous in scientific history. Yet Bohr remained steadfast. He did not claim that quantum mechanics revealed an ultimate truth, only that it described what could be known. Beyond that, he said, language and reason simply failed us. In time, the Copenhagen interpretation became more than a theory. It became the philosophical backbone of modern physics. It shaped how generations of scientists approached the mysteries of the microscopic world. It taught that understanding does not always mean certainty, and that the limits of knowledge are not weaknesses but reflections of our place within the universe. Through the Copenhagen interpretation, Bohr gave humanity a new lens to view reality, one that embraced paradox and accepted uncertainty as natural. He reminded the world that science is not the conquest of mystery, but the respectful dialogue with it. His vision endures not just in the equations of physics, but in the spirit of inquiry itself, the courage to question, to wonder, and to accept that even the smallest particle holds within it the vast poetry of the cosmos. When the Second World War cast its dark shadow across the globe, Niels Bohr found himself standing at the intersection of science, politics, and humanity. His fifth great contribution to modern physics was not made in the laboratory, but in the moral and philosophical struggle that came with the discovery of nuclear fission. The world that quantum physics had helped unlock was now capable of unimaginable power, both creative and destructive. Bohr, who had once looked into the atom for truth and understanding, now saw within it the potential to destroy civilization. His life's mission began to evolve from scientific discovery to the responsible use of knowledge. In 1939, when news reached Bohr that German scientists Otto Hahn and Fritz Strassmann had succeeded in splitting the uranium atom, he immediately grasped the magnitude of the discovery. It was the physical proof that Einstein's famous equation, E = mc Gauss, could be unleashed in reality. A small amount of mass could indeed be converted into an enormous amount of energy. Bohr understood that the world had just entered a new era, the atomic age. But unlike others who saw power or opportunity in this revelation, Bohr saw a deep and dangerous responsibility. He knew that such knowledge could never again be confined to laboratories or academic journals. It had the power to reshape nations, politics, and the fate of humanity itself. Bohr's moral instincts were as strong as his scientific curiosity. As Europe burned in war and the Nazi regime spread terror, he was forced to flee his homeland. Denmark was occupied and Bohr, part Jewish through his mother, was at risk. With the help of the Danish resistance and British intelligence, he escaped to Sweden, then to England, and finally to the United States. There he joined the Allied efforts, working briefly with scientists at Los Alamos, the heart of the Manhattan Project, where the first atomic bomb was being built. But Bohr's role was unique. He was not a designer of weapons, he was a conscience among creators. Bohr urged openness and international cooperation, even in wartime. He believed that secrecy would only lead to fear and mistrust, and that the world's best hope for peace lay in mutual understanding. He warned that once the atomic bomb was built, it could not remain a secret forever. He argued that nations must share knowledge about nuclear power, not to build more weapons, but to build trust. To him, the control of atomic energy was not a technical challenge, it was a moral one. Science, he said, had connected humanity more deeply than ever before, and that connection carried a duty to act with wisdom and compassion. While many around him focused on victory and survival, Bohr looked beyond the war. He saw that the true danger would come after the fighting stopped, when nations, armed with atomic knowledge, would turn suspicion into policy. In 1944, he met with British and American leaders, including Winston Churchill and Franklin D. Roosevelt, to advocate for what he called an open world. He envisioned a future where scientific knowledge was shared transparently, where communication replaced conflict, and where science served as a bridge rather than a weapon. But his idealism was met with resistance. Churchill, cautious and secretive, accused Bohr of naivety. To Bohr, it was not naivety but foresight. He understood, before most, that the atomic bomb would forever change geopolitics. When the war ended with the bombings of Hiroshima and Nagasaki, Bohr was devastated. The weapon born from the atom, the very atom he had helped humanity understand, had brought unprecedented destruction. He mourned not only the lives lost, but the meaning lost. Science, he believed, had been used without wisdom. From that moment, his mission became one of reconciliation, between nations, between science and society, and between knowledge and morality. He dedicated his later years to promoting peace and cooperation in the nuclear age. In 1950, Bohr wrote his famous, Open Letter to the United Nations, a passionate plea for transparency and dialogue in the atomic era. He urged world leaders to replace secrecy with honesty, competition with collaboration. He argued that the survival of civilization depended on humanity's ability to rise above fear and division. His letter was both scientific and spiritual, a call for a new kind of politics grounded in the humility that quantum theory itself had taught him. Just as the atom could not be understood without recognizing the role of observation, the world could not find peace without mutual understanding. Bohr's moral stance earned him admiration and frustration in equal measure. To some, he was a visionary; to others, an idealist out of step with the real world. Yet history has proven that his warnings were prophetic. The arms race that followed the war mirrored exactly what Bohr had feared: a world divided by suspicion, each nation holding the power to end life on Earth. But Bohr's voice never ceased to call for balance, reminding humanity that knowledge without conscience is peril. In his later years, Bohr returned to Copenhagen, where his institute continued to be a beacon of intellectual and moral inquiry. He surrounded himself with young scientists, teaching them not only equations and experiments but also empathy and responsibility. He spoke often about the complementarity between freedom and security, between progress and peace. To him, these were not contradictions but essential partners in the survival of civilization. The same principle that governed quantum mechanics, the unity of opposites, he now applied to human affairs. Niels Bohr's legacy in this moral and political chapter of physics was profound. He showed that science is not separate from humanity, but deeply intertwined with it. The discovery of atomic energy had revealed both the greatness and the danger of human curiosity. Bohr's voice stood as a guiding light, reminding the world that understanding nature's power demands moral clarity. His courage to speak truth to power, even in times of fear, made him not just a scientist of atoms but a philosopher of peace. By the time of his death in 1962, Bohr had lived through 2 world wars, a scientific revolution, and the dawn of the nuclear age. Through it all, his belief never wavered that communication and cooperation were the only true paths forward. The atom had taught humanity that everything is connected, that observer and observed, cause and effect, science and society, are threads in the same cosmic fabric. Bohr's final message was not one of despair but of hope. He believed that the same spirit of curiosity that led to the atom's discovery could also lead to a wiser world. In his vision, the power of the atom was not just a threat. It was a mirror, reflecting what humanity could become if it chose wisdom over fear, unity over division, and understanding over destruction. In the years following his greatest scientific triumphs, Niels Bohr became not only a physicist, but a philosopher of nature, a man whose influence stretched beyond the walls of laboratories and into the consciousness of humankind. The 6th keynote of his legacy lies in how his ideas reshaped not just quantum physics, but the very way scientists, philosophers, and thinkers approached knowledge, reality, and the human experience itself. Bohr's impact went far beyond equations or experiments. It became a guiding philosophy for an age of uncertainty, complexity, and connection. He did not just help build modern physics. He helped redefine how humanity understood truth. Bohr's concept of complementarity, born from the paradoxes of quantum mechanics, became one of the most profound ideas in 20th century thought. It taught that 2 seemingly opposite descriptions could both be true, depending on context. Just as light could behave as both a particle and a wave, truth itself could have dual aspects. This was not simply a principle of physics, it was a philosophy of life. Bohr believed that all knowledge, whether scientific, moral, or human, was shaped by perspective. There was no single, objective picture of reality. Understanding came only when different viewpoints were seen as complementary rather than contradictory. This vision resonated deeply with thinkers in psychology, art, and even theology. The world was no longer a machine of absolutes, it was a web of relationships. Throughout the 1930s and 1940s, Bohr's Copenhagen Institute became more than a center for physics. It was a sanctuary for dialogue. Scientists from across the globe gathered not only to discuss equations, but to explore the meaning behind them. Conversations would drift from atomic structure to the nature of consciousness, from probability in physics to uncertainty in human decision-making. Bohr's quiet presence guided these discussions. He rarely gave direct answers. Instead, he asked questions that led others to discover truth for themselves. His humility was legendary. He once said that the opposite of a profound truth might also be true, a reflection of his belief that knowledge is always incomplete, and wisdom lies in recognizing its limits. This intellectual openness influenced a generation of scientists who carried his ideas far beyond quantum theory. His students and collaborators, such as Heisenberg and Pauli, became giants of their own, yet they all carried within them Bohr's spirit of inquiry, the balance between precision and wonder. Bohr's influence extended into philosophy through his correspondence with thinkers like William James and his resonance with Eastern thought, particularly the paradoxical insights of Taoism and Zen Buddhism. Without intending to, Bohr had built a bridge between Western rationalism and the intuitive philosophies of the East. In a world that often sought simple answers, he celebrated complexity as a sign of truth's richness. As the atomic age progressed, Bohr became a symbol of responsibility in science. He never saw knowledge as something to be owned or controlled, but as something to be shared, questioned, and respected. He warned against the arrogance of certainty, urging that science must remain grounded in humility. For Bohr, the mystery of the quantum world was not something to be conquered, but something to be understood through cooperation with nature and with one another. His belief in open dialogue extended into his vision for humanity itself. The principle that no one observer could see the full truth of an experiment became, in his eyes, a metaphor for nations and people. Only by sharing perspectives could the world approach reality as a whole. This humanistic dimension of Bohr's thought made him one of the rare scientists whose influence touched both science and ethics. He saw parallels between the complementarity of quantum mechanics and the complementarity of human values, freedom and order, individuality and community, competition and cooperation. He believed that just as particles could not be described without reference to measurement, humanity could not progress without reference to understanding. His philosophy suggested that unity was not the absence of differences, but the harmony between them. The universe, he believed, was built not from simplicity but from balance. In his later years, Bohr's reflections deepened into a kind of quiet wisdom that transcended physics. He often spoke of how the mysteries of the atom mirrored the mysteries of life. The more deeply we look into the fabric of reality, he would say, the more we realize that we are part of it, that the observer and the observed cannot be separated. To him, this was not only a scientific insight, but a moral one. It meant that humanity's actions, thoughts, and choices were all intertwined with the universe itself. Knowledge carried responsibility because knowing and being were one. Even as technology and industry raced forward on the foundations of his discoveries, Bohr remained a voice of reflection amid progress. He warned that science without wisdom could lead to imbalance, just as measurement without interpretation led to confusion in quantum theory. His philosophy urged balance between curiosity and conscience, invention and reflection. He dreamed of a world where the pursuit of truth was guided not by power or profit, but by understanding and harmony. This vision, though idealistic, continues to inspire scientists and thinkers to this day. When Bohr passed away in 1962, his funeral was attended not just by physicists, but by philosophers, statesmen, and students who saw in him something greater than a scientist. He had become a symbol of what it meant to think deeply and responsibly about the mysteries of existence. His words and ideas continued to echo long after his death, reminding the world that knowledge is not just a tool, but a relationship. Every discovery, every observation, is a conversation between the human mind and the cosmos. The enduring power of Bohr's sixth great contribution lies in this realization that science and philosophy are not separate realms, but parts of one great quest to understand who we are and what reality truly means. Through his ideas, the modern world learned that truth is layered, that knowledge is dynamic, and that uncertainty is not the enemy of understanding, but its foundation. Bohr transformed doubt into wisdom, contradiction into beauty, and the quantum into a mirror for the human soul. His legacy is not merely in the textbooks of physics, but in the way we think, question, and dream about the universe itself. As the final chapter of Niels Bohr's remarkable life unfolded, his seventh and lasting legacy became clear. He had reshaped the human understanding of knowledge, responsibility, and the delicate harmony between science and society. His work had begun with the mysteries of the atom, but by the end of his life, Bohr had become a bridge between worlds, between the microscopic and the cosmic, between theory and philosophy, and between scientific progress and human morality. His story is not only that of a physicist, but of a man who saw deeper than equations, who understood that the pursuit of truth is also a pursuit of wisdom. Bohr's final years were spent reflecting on the vast consequences of the quantum revolution he had helped unleash. He had watched humanity step into an age of unprecedented power, an age where the same discoveries that illuminated the inner workings of atoms also gave rise to weapons capable of annihilating cities. It was a moment of triumph and tragedy, and Bohr's voice emerged as one of calm reason amid the rising storm of the Cold War. He believed that science could no longer exist in isolation. The discoveries of the 20th century had bound knowledge and ethics together forever. To him, it was not enough to understand how the universe worked. One must also understand how that knowledge would shape the destiny of humankind. In his view, the same principles that governed the atom governed human civilization. Just as particles could not be separated from the act of measurement, nations could not be separated from the consequences of their choices. Bohr's complementarity, the idea that opposites are not contradictions but parts of a greater whole, became a metaphor for coexistence. He saw democracy and security, freedom and order, competition and cooperation as complementary forces necessary for balance in the world. His wisdom extended beyond laboratories into the moral and political fabric of modern life. He spent his last decades tirelessly advocating for openness, communication, and shared understanding between nations. His vision of an open world, first articulated during the development of nuclear weapons, became the centerpiece of his humanitarian philosophy. Bohr's influence on the post-war world was both subtle and profound. Though he held no political office, his thoughts shaped global discussions about atomic energy and international relations. He met with scientists, diplomats, and leaders, encouraging them to think not as adversaries, but as partners in a common experiment, the experiment of civilization itself. He believed that the survival of humanity depended on learning from the same humility that quantum mechanics had taught physics, that no single perspective could ever reveal the whole truth. Cooperation, like observation, was not optional. It was the only path to understanding. In his lectures and writings, Bohr often returned to one central idea that science, at its best, was a dialogue between the human mind and nature. It was not about domination or control, but about relationship. The scientist's role was not to conquer the unknown, but to listen to it, to interpret it, to find harmony within it. This philosophy shaped not only the future of physics, but the culture of scientific thought itself. Under Bohr's influence, generations of researchers came to see their work as part of a larger ethical framework. He reminded them that curiosity must walk hand in hand with conscience, and that the power of knowledge must always be tempered by the wisdom of restraint. In the twilight of his career, Bohr began to see his scientific principles reflected in the broader human condition. The uncertainty that governed quantum mechanics was mirrored, he thought, in the uncertainty of human life. We live, he said, not in a world of fixed truths, but in one of possibilities, of potential outcomes that depend on our choices and actions. To Bohr, this realization was not a cause for despair but for hope. It meant that the future was not predetermined. Just as an electron's position is not fixed until observed, the future of humanity was not fixed until chosen. Our fate, he believed, was still an open question, and the answer lay in how we observed, acted, and understood one another. Bohr's home in Copenhagen, once the center of the quantum revolution, became in his later years a place of quiet reflection. Visitors recall him as kind, thoughtful, and endlessly curious, a man who never stopped asking questions, even about the simplest things. He would walk through his garden speaking about the unity of nature, or sit for hours discussing how science and philosophy were two languages telling the same story. To his students, he was not merely a teacher of physics but a mentor of thought. He urged them to see beauty in paradox, to find truth in uncertainty, and to never lose sight of the moral dimensions of discovery. Even after his death in 1962, Bohr's influence continued to shape the intellectual world. The principles he helped establish, quantum theory, complementarity, and the philosophical framework of modern physics, became the foundation of technologies that now define human civilization. From computers and electronics to lasers and quantum communication, the fingerprints of Bohr's ideas are everywhere. Yet, beyond the technology, his true gift lies in the way he taught humanity to think. His work transformed science from a mechanical pursuit into a reflective one, connecting the physical and the metaphysical, the measurable and the meaningful. Bohr's final message to the world was one of unity through understanding. He believed that the divisions that separated people, nations, and ideologies were illusions, born from the same limited perspective that once blinded science to the quantum truth. Just as nature revealed her secrets only through the coexistence of opposites, humanity could progress only through cooperation between differences. He saw in science a mirror of society, a vast, intricate system where every part, however small, affected the whole. In the end, Bohr's greatest legacy was not a single discovery, but a way of seeing, a way that blended logic with humility, intellect with empathy, and knowledge with wisdom. He taught the world that truth is not a weapon to be wielded, but a relationship to be nurtured. His life was proof that science could be both a path to power and a path to peace. He had illuminated the invisible, but more importantly, he had shown that understanding the invisible required understanding ourselves. Through the legacy of Niels Bohr, the story of modern physics becomes the story of humanity's awakening to its own dual nature, brilliant yet fragile, curious yet fearful, powerful yet uncertain. He reminded the world that every equation is a question, and every discovery a reflection. The quantum world, he taught, is not separate from us. It is us, in motion, in interaction, in mystery. And as long as we continue to question, to seek, and to wonder, we carry forward the spirit of Bohr himself, the quiet genius who taught the world that the deepest truths of the universe are written not in certainty, but in understanding.